Rockets are violent, unstable machines. Without control, they don't fly. They crash, flip, or lawn dart at Mach 2. Conventional model rockets use fins for stability. These provide aerodynamic stability while ensuring the rocket maintains a stable and straight path of flight. But what if we remove the fins? We don't use them. Like in real rockets, you rarely see fins used to keep it straight. But how do we actually control a rocket then? Not just make it go up, but keep it straight, aim it, and even land it with precision. In this video, I'll explain the two control systems I've used or plan to use in my own rockets: PID and NMPC, or Proportional Integral Derivative and Nonlinear Model Predictive Control. Let's go. At the core, a control system takes sensor data, for example, orientation or velocity, and calculates how you can adjust the rocket's actuators in order to counteract this change and ensure that the rocket maintains a stable path of flight. This is essentially what's called a control loop, measuring something, actuating, getting feedback, and then doing it again, and again. These loops run dozens or hundreds of times per second in order to maintain this path of flight. Now, there are two ways of doing this. The first one, PID. This is classical control theory. Many people have used PID effectively to keep rockets straight. It's quite simple in theory and consists of three different terms: proportional, integral, and derivative. I won't be going into the details of how this exactly works, but many videos and resources can be found online in understanding how it works. What you need to know is that it's reactive, it's classical, it's not computationally intensive, and it works. It's reliable. On the other hand, enter NMPC. But what is NMPC? You may have never heard of this before. Well, NMPC is the big brain. It doesn't just react, it predicts the future. But for this to work, you need to know how would the rocket behave. What NMPC does is it simulates the rocket's behavior based on its physics, i.e. you have a model of how the rocket behaves, and it chooses the best control inputs possible in order to minimize your drift and how much you need to actuate. The good thing about NMPC, it factors in system dynamics, so you could have complex aerodynamic equations and get an accurate overview of your system, your limits on thrust, gimbal angle, or servo speed. Now this is crucial. For example, if you were banking at a 45-degree angle or more in PID, the appropriate control response may be too large for your control system to handle. For example, a servo with a gimbal range of plus minus 5 degrees will not be able to take a control input of 10 degrees. This could lead to catastrophic failure, but NMPC handles this. What it does, it checks your deflection range of servo angles, your gimbal angles, and also your servo speed. You can also see your desired future state. So it's not just to keep a rocket straight. You can make it go where you want, essentially called waypoint guidance in the air, which is crucial for future flights that incorporate precision landing. But the trade-off is computationally expensive. And when I mean computationally expensive, I don't mean that you can't use an Arduino and you need a Teensy. I mean that you need dedicated processors to running it. On my rocket, what will run it is the CM4. It's the Raspberry Pi CM4, a compute module that would be fully dedicated to running nonlinear model predictive control. Now, even with this much power, you still have to be smart about how you code it, because you're solving a problem 50 times a second while a rocket's falling out of the sky. So now that begs the question, when do we use PID and when do we use NMPC? They both are good, but they have their own trade-offs and benefits. So see, early test flights of a rocket should utilize PID because it's simple, it's not computationally expensive, and it's not even that hard to code. On the other hand, if you want precision landing, propulsive landing, or even catching a rocket with chopsticks, you have to use NMPC. This gives you full control of system dynamics, awareness of constraints, and most importantly, prediction, which means you don't react, you are active. In final thoughts, control theory is what turns a rocket from basically a firework into a precision machine. PID is where you start, and NMPC is the ultimate end goal for amateur rocketry. And this is just the beginning. You can even combine NMPC with things like neural networks to tune the weights of an NMPC module, effectively making it the best control system possible. If you're working on your own project, like I am, test PID first, and then when you're ready, try NMPC. I'll be doing the same. Thanks for watching. Subscribe if you want more real rocket engineering. That's it for today. Thank you.